This is part 2 on finding the area between two curves. In part 1 we talked about the idea behind finding the area and did a few examples. And in part 2 we'll look at maybe 5 more examples. So the first one, we're considering the area that's bounded by x equals 0 and the first intersection of y equals sine x and y equals cosine x. Again, it's generally a good idea to sketch a picture so you know what's going on. I know that x equals 0 is the y-axis, that sine x starts at 0, goes up to 1, and it gets to 1 at pi halves, and then goes back to 0 at pi. I know that cosine of x starts at 1 and heads down to pi halves. So what I need to do is figure out what is this point of intersection. When does that occur? What I want to know is when does sine x equals cosine x? And any of you that have me for Algebra 2 should know, because you have memorized that trig chart, that this occurs when x equals pi fourths, or 45 degrees. You should know this point of intersection. Since we know our point of intersection, then what we're looking at is this region here, which in terms of x starts at 0 and goes to pi fourths. So those are our limits of integration, from 0 to pi fourths. Now in this case, our upper limit, our upper curve is cosine x, and it's always minus your lower curve, which in this case is the sine of x dx. When we integrate this, the integral of cosine x is sine x. The integral of negative sine x is cosine x, and we will be integrating this from 0 to pi fourths. And it is expected that you would know your basic trig identities, that they should be memorized, right? So it's expected that you know sine, cosine, tangent, secant, cosecant, and cotangent for 0, pi sixths, pi fourths, pi thirds, pi halves, and everything else related to those around the unit circle. If we substitute in pi fourths, the sine of pi fourths is root 2 over 2. The cosine of pi fourths is root 2 over 2. Minus the sine of 0 is 0. The cosine of 0 is 1. And so altogether, this would be the square root of 2 minus 1 for our area under the curve. Let's consider another example. We'd like to find the area between these two curves, a cubic and a quadratic. And if we were to graph these, we're going to see something that looks roughly like this. We've got a cubic doing something basically like this, and the quadratic doing something like this. So we can see that they intersect at 3 locations, though I don't know exactly what they are. The second thing to notice is that I'll call the cubic y1 and the quadratic y2, that for part of the time the cubic is on top, and for part of the time the cubic is on the bottom. So we're going to need 2 different integrals because they change which one's upper and which one's lower. We need to find the points of intersection. We want to know when is 2x cubed minus x squared minus 14x equal to 4x minus x squared. Bringing everything over, we want to know when is 2x cubed minus 18x equal to 0. When is 2x, factoring this out, times x squared minus 9 equal to 0. This occurs at x equals 0 and x equals plus or minus 3. So this gives us our limits of integration. We're ready to set up our 2 different integrals. In our first integral, from negative 3 to 0, The cubic is our top equation, so I want to integrate what I've labeled as y1 minus y2 with respect to x. And then for my second integral, they've changed which one's the upper integral, so I'm going to integrate y2 minus y1 in that case. And again, that's dx. I just use y1 and y2 to save myself some writing. When I integrate y1 for my first integral, I'll end up with, what's that going to be? One half x to the fourth minus 1/3 x cubed minus 7x squared. That'll be minus my lower curve, so when I integrate 4x, that should be 2x squared minus 1/3 x cubed. That needs to be evaluated from -3 to 0, plus, now I'm just going to end up reversing these two things, 2x squared minus 1/3 x cubed minus 1/2 x to the fourth minus 1/3 x cubed minus 7x squared, and this gets evaluated from 0 to 3. Before I evaluate these, I'm going to clean them both up a bit. So my first equation will simply be 1/2 x to the fourth, the 1/3 x cubed dropped out, minus 9x squared from -3 to 0. Hopefully I left myself enough space. Plus, we'll have -1/2 x to the fourth. The 1/3 x cubes drop out, and we're left with plus 9x squared from 0 to 3. Some substitution. My upper limit is 0, so everything's going to drop out. So this will be 0 minus, when I substitute in -3, this will be 81 over 2 minus 81 plus, for my second integral, when I substitute in 3, this will be -81 over 2 plus 81 minus 0. And cleaning everything up, what will this end up being? Let's see, for the first part it'll be 81 over 2 plus another 81 over 2. So altogether we get a total area of 81. And there you have it. Let's look at one more example in this part 2. So in part 2, we want to find the region that's bounded by all three of these graphs. So doing a rough sketch, 12 minus x squared is this parabola. Do something like that. Y equals -x is this line. It's doing something like that. And y equals 4x is this line. It's doing something like that. So what we want to do is find this baseball field looking shape. We do need to find our 2 points of intersection. And so one of them, we want to know when is 12 minus x squared equal to -x. And our second one, we want to know when is 12 minus x squared equal to 4x. Let me solve these real fast. So I've solved both equations, and I can see just based on my graph that my first point of intersection is at x equals -3. My second point of intersection is at x equals 2. Now the other thing I need to notice is that I can see that my two lines cross at the origin, and that's when there's a shift in what ends up being the lower curve, right? -x is the lower curve in here. Let me sketch it in red. And 4x is the lower curve here. So we're going to have two different integrals because there's two different lower curves for my area. So my first integral in this case will go from -3 to 0, and the upper curve is 12 minus x squared, and the lower curve, so minus the lower curve, which is -x. I'm going to add to that the area from 0 to 2, and in that case the upper curve is still 12 minus x squared minus the lower curve, which is different. In this case it's 4x. And when I integrate these two things, I end up with 12x minus 1/3 x cubed. Since that would be plus x, when I integrate that, that'll be 1/2 x squared from -3 to 0. And I'll add to that what I get. So let's see, 12x minus 1/3 x cubed minus 4x, so that would have been minus 2x squared. This one is from 0 to 2. If I evaluate these, first part it'll be 0 minus, substitute in -3, so that's -36, what's that, -27, so plus 9 over 2, plus, substitute in 2, so this will be 24 minus 8/3 minus 8, and I'm substituting in 0 again, so minus 0. This is a funny looking 0, but it is a 0. And when I combine all of these things, I get an area of 215/6. There we have it. And in our final video, we'll look at two more examples of finding the area between two curves.